everyone. My name is Emma. The thing I'm going to talk about is like a really narrow topic compared to like the history that we just learned. I'm just going to talk about like one particular material, and that material creates local Curie temperatures. So the reason that we care about this is because, like, in general, like for normal material that we have, the ferromechanism is more like a long-range general bulk type of feature. So, but like we do want some like special property on like some small region. So that's why we want to create some like local spatial variations of the magnetic properties of the ferromagnetic materials. And one thing that we can do is the local Curie temperatures. And so having a different Curie temperature, we learned, is like the temperature that changed from paramagnetism to ferromagnetism. And having like a different local Curie temperature will help us like create like different magnetic region, like a small magnetic region that's at the same temperatures compared to the first. Okay, so the way we're gonna make it is we're gonna use a varying exchange strength, exchange energy. So the pattern of the exchange coupling strands that we want is like a V-shaped type of pattern. So it goes up, it take at a center, and it goes down. And to actually enact that in the material, we use this structure. This is what we have. Like all the other patterns here is just to stick with it, but this one is where we actually create this like this V shape of the exchange energy. So the way we did that is we changed the rate that the ruthenium is in the cobalt-ruthenium alloy. So, and here they did a periodic structure, but like we can also just pick one. And having a periodic structure doesn't change much. It's just like periodic is going to be bonded and just going to repeat periodically. And so there's like, so we can have the change, and we can look. One thing we can change, one direction would be the rate that this exchange stress changes. So if the length between the ratio distribution is large, then it changes slower. And the change rate is going to affect like how locally we can have our magnetic field and like magnetization, and also the Curie temperature difference that we can get. Okay, so this is the actual data that's measured from the previous setup. So the gray one is the smaller, the faster change one, and the blue one is the slower change one. And we can find that like at the bottom, like remember we have a V shape of the exchange strands. At the lower side, like where we have smaller exchange strands, you have a lower Curie temperature, and top you have a higher Curie temperature. So like the in between the Curie temperature actually varies. And we change the modulation in Curie temperature, the Curie temperature modulation, and it's delta Tc. And the value is shown here. We do have a pretty large change, like not pretty large, but like a decent change in the Curie temperature compared to what are we saying? Okay. And so that's our actual data, and we want to check if that fits our model. So the way we simulate that is we use the mean field approximation of the Ising model. Ising model is like static magnetism, statistic mechanism at a heat type of thing. And basically from that simulation, we write this equation and we cut this our wave shift into multiple small pieces, and for each piece, the magnetization inside is that, like we divide it into L1 right here. And like we remember we have here around saying it's just another piece. So, and we using the simulation, the result that we got is actually is right here. So our Curie temperature modulation was this curve here. So this d length here is the distance from the center to the other parts, and so as it's closer or closer to the peak, then you have a larger change, like away from the Curie temperature. And for this one that has a larger distance, the change is actually larger, like it can change for a longer range. And the change, the velocity change rate is 3 nanometers. So it's pretty small. So we can create a difference in Curie temperature in a very small region. Okay, so after we have different Curie temperature, then we apply magnetic field, when we create a different temperature, they will create different magnetization. Right, so the S here is the inverse of the d dimension. This really is the rate of change, and it's the same as what's previously here, right? You have a larger d and have a smaller s. You have a more obvious change, because like the range like does change more, because originally when it's zero, it means like it's the same as T, our original Curie temperature. So if you have a larger D, you're gonna have a range that have a different Curie temperature compared to the original one. And this is the magnetization graph. So we see that we actually have like local magnetization that's different from the average, and just due to different temperature that we apply. And like this will have a lot of different application. It's creating a small region of magnetization in a small range, which that's why we want like a local Curie temperature, local thing, instead of like the original bulk property that we have. And that's it. Any question?